Okay, so we're going to look at exponential decay today. I need you to make one correction. Instead of exponential growth, that should say decay right there. So go ahead and make a correction there.
Are you recording?
Yes. Exponential decay can be modeled with the function y equals a times b to the x, for a is greater than 0 and b is greater than it's greater than 0 but less than 1. You need to put a 1 on there. Now, here's how you tell the difference. The two functions are exactly the same for exponential growth and decay. The only difference is with exponential growth, your b is going to be greater than 1. So the b is the number, the second number in the equation. So if that number is bigger than 1, we know it's an exponential growth. If that number is less than 1, then it's going to be decay. So that's how you can tell the difference in the two, because there are some questions in your homework that are going to ask you if it's growth or decay. All right, and that's how you can tell. Before we get into some of the problems like what we had yesterday, what we're going to first look at is something called half-life. Half-life is the time required for something to fall to half its initial value. Let's say, for instance, we have 30 milligrams of some substance. I don't know what the substance is, but let's say we have 30 milligrams of some substance. And the half-life for it is 3 days. What that means is in 3 days, that 30 milligrams will be cut in half. So after one half-life of 3 days, you would have 15 milligrams of the same substance. That's what a half-life is. It's the number of days or hours or minutes. It's some unit of time that passes, and then half of the substance is left. We could go through another half-life. Let's say it's been 3 days and we now have 15 milligrams, right? Let's say we go 3 more days. What would be left there? 7.5. We cut that in half. Do you see what I mean? It's like you keep halving it. So
dividing by 2 each time?
Yes, dividing by 2 each time. So that's what a half-life is. Those of you that have Miss Tackett, if you go in and tell her about half-lives and you know what a half-life is, she'll be really impressed and pretty excited. Christina's already learned about half-lives in Miss Tackett's class. So she'll be pretty impressed if you can start talking about half-lives, you know. She likes that chemistry stuff, you know. All right, listen. The half-life of a radioactive substance is the length of time it takes for one half of the substance to decay into another substance. We already talked about that. That's what I just told you. To treat some forms of cancer, doctors use radioactive iodine. The half-life of iodine, and 131, that's just the type of iodine it is. Okay? So that has nothing to do with the math part of it. It's just, it's iodine 131 is what the substance is called. This substance has a half-life of 8 days. That means it takes 8 days for half of that substance to go away. All right? So we have a substance whose half-life is 8 days, and that half-life could vary depending on what kind of substance it is. This one in particular is 8 days. So if we look at this, letter A, it says how many half-lives of iodine 131 are in 32 days? So how many half-lives exist in 32 days? 4. You have 4 half-lives because,
How do you know that?
well, the reason I know that is because one half-life is 8 days. So you do 32 divided by 8.
But earlier we did it in 3 days each time.
I know, but listen, a half-life, the length of a half-life, it depends on what kind of substance it is. My example I used up here had a half-life of 3 days. This one actually has a half-life of 8 days. It depends on the type of substance. So this has a half-life of 8 days. So for this particular iodine 131, its half-life is 8 days. So in 8 days, whatever substance, however much you have of it, in 8 days will be half.
Okay.
Okay? Yes, Kylie.
So it'll vary problems or something.
It won't always be the same amount of time, right? It could be hours, it could be days, it could be minutes, honestly. In one of your problems in your homework, it's 20 minutes. It's got a 20-minute half-life. So in 20 minutes, half of it's gone. So, now let's look at an example with a number here. If a patient receives 12 MCI, MCI is just a unit of measurement for radiation. Let's say they get a 12 millicures treatment of iodine-131. How much would be left in a patient's system after 16 days? How many half-lives is 16? 2 half-lives. So here's how I visually represent it. This, if you visually represent it, here's 1 half-life, and here's 2 half-lives, okay? Put the starting amount on the upper left side of this. Put the starting amount. We started with 12. We started with 12 millicures. After 1 half-life, how many millicures are going to be left? 6. Then after another half-life, 3. So we have 3 millicures left. So that's basically what you do, is you just keep halving it, depending on how many half-lives you have. If you have 4 half-lives, you divide by 2 4 times. So you get to the answer. Yes, Ben?
So theoretically, you would never run out of radioactive iodine.
That is correct, Ben. That's actually a really high order thought that you just had. Because in chemistry, or not chemistry, in calculus, we talk about limits. And an example that you could think of is if I started right here and made half the distance, moved half the distance to the wall, and then I did it again, and then I did it again, would I reach that wall?
Yes. No. I don't know. I would go
See?
beyond the wall.
It's like cutting a piece of paper in half.
Right. Well, you never. Right. Exactly.
Never do it.
But anyway, that's something. That's a concept that when you guys become juniors and seniors and you start taking calculus, this will make a lot more sense to you. But right now, we're just gonna stick with half-lives. How about that? Yes, Chance.
If you started off with 12,
Yes.
and say you waited about an hour or so, and then you had 6, another hour, that 6 would be gone. True or false?
It'd be 3.
False. Well, it's not an hour. A half-life is 8 days.
So it would slow down and quit deteriorating so quickly over time.
Well, sort of. Okay, guys.
So you start with 12.
Okay, guys, let me go over this concept one more time. Let's go over this one more time. Look, if you visually represent it, 8 days is 1 half-life. 8 days is 1 half-life. So here's 8 days has passed. Here's after 8 days. And then here's another 8 days, which equals 16 days, right? All right, so if we go 1 half-life, a half-life is after that half-life passes, the number of days passes for the half-life, half of that substance is gone. It goes from 12 to 6. Then another 8 days, another half-life, and it's down to 3. So we're halving it and then halving it again. Basically, you find out this number here, like we found out there were 2 half-days. Half-lives. You find out there are 2 half-lives, and then basically you're going to take 12 and divide it by 2 twice. And then you get 6. And then we divide it by 2 again, and you get 3. And that's how we came up with the 3. Yes, Jenny?
Why is there 14 and 24? Oh, wait, never mind. That's
Okay.
Stupid.
Okay. Example 2. All right, example 2. Since 1980, the number of gallons of whole milk per person in the United States, or each person in the United States drinks every year, has decreased 4.1% each year. In 1980, each person drank an average of 16.5 gallons of whole milk in a year. Okay? We're going to write an equation that models the gallons of whole milk drunk per person. Now, the equation to this is y equals a times b to the x, where a is our starting amount still, our starting amount. B, however, we now call, b equals what we call a decay factor. We called it a growth rate yesterday. Today it's called a decay factor. It's called it, I do, yes. Don't drink whole milk, though. I drink skim.
What about cheese?
Yes.
That's whole milk.
So, this right here, this B is going to be what's called your decay factor. And there are, again, going to be some problems in your homework that just says, what is your decay factor? So all you have to do is look at the equation, pick out B, and that's your growth rate. And that's all you got to do. That's like numbers two of the problems, 22 and 24. I've helped people with that all day. It's just picking out your B, picking B out of an equation. Okay, now, to find the decay factor, you take 1 and you subtract from 1 the percent that they give you as the decrease. So, but we can't just put 4.1. We have to deal with the percent in a decimal form. So what is that percent in decimal form? 0.041. So it's 1 minus 0.041, and that's going to give you your decay factor. So instead of adding 1, you're now going to take 1 and subtract the percent from it. So your percent, this number is going to be lower than 1. It should be less than 1, your decay factor.
It's -1, isn't it?
No. It's 1 minus 0.041. Yeah, it's 0.959. That is your decay factor. So our equation then becomes y equals, what's our starting amount? 16.5. If you look up here in the problem, in 1980, each person drank 16.5 gallons per year. So 16.5 is the starting amount. And then we multiply it by our decay factor, which is 0.959, raised to the x power. This is our equation. That's our equation to model the amount of consumption of whole milk. Now we're going to use that equation for B. We're going to use the equation y equals 16.5 times 0.959 to the x power.
Wouldn't it be 20 because 20 years have passed since 1980?
Yes. Let's look at what it's asking. Use your equation to find the approximate consumption per person of the whole milk in 2000. So the years, how many years it's been? It's been from 1980 to 2000. That's 20 years. So we're going to plug 20 in for x. So we get y equals 16.5 times 0.959 to the 20th power. And you can put that right into your calculator. And y equals, what is it? 7.14. So 7, we'll just round it to the nearest 10. 7.1 gallons. So in 2000, the average person consumed 7.1 gallons of whole milk.
I think I drink that maybe.
Yeah.
I'm probably well under that amount, I bet.
Me too. I don't
Skim
drink
milk really isn't.
I drink milk like
It's just
I think
water
it's milk.
with milk flavor.
I know.
White food coloring.
But like Levi said, if I eat cheese, that's whole milk, right?
Do you eat cheese?
Yeah. I had cheese pizza just a little while ago.
That's not meat.
You might as well just drink whole milk.
It doesn't make a
Miss
difference.
Dixon,
You're not eating it.
Yeah, you're not eating the cow.
Yes.
Are you still recording?
You're mooching off.
Okay. So it's 7.1 gallons of milk, and that is how you find, or that's how you use exponential decay.
Is that it?
That's right.